Hello guys and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're continuing the problem that we stopped on the last video, and we were looking at the situation in which we have these three spheres rotating about ring G, and the ring dissolves outwards, allowing the spheres to go each to different directions. Let's have a look at the video once again just to remind ourselves of what's going on. The ring dissolves and then the spheres are free to move to different directions. Now, once again, remember that not only the ring is moving to the right, but also the balls are rotating about G. So there's a couple of things happening there at the same time, right? Now, we are interested in finding out what is this distance D because everything else we found already. So problem statement is that we have three spheres. They're rotating about ring G. That was horrible. The distance from the ring to the sphere is 200 millimeters. That is 0.2 meters. And there's an initial velocity of 0.4 of this guy here. And then the initial part of the problem was actually finding out what is the velocity for the different spheres. And we found out that this guy here is 0.693 meters per second. We found out that B is exactly the same as A, but on the opposite direction. And we found out that C is just 3 times the rightwards momentum that we had, rightwards velocity, because we're converting, the linear moment has to be conserved, and we have the threefold decrease in mass. So we have a threefold increase in velocity. So we know all the velocity already. The only unknown at the moment is this distance d here. Now to do this, what we're going to do is we're going to use the conservation of angular momentum. If we recall, the way that this problem went is that we had all these unknowns. So we had these three unknowns here. And then to solve these three unknowns, we use these three equations. So we use the linear momentum conservation on the x direction, then we use the linear momentum conservation on the y direction, and the energy conservation. And with these three equations, we're able to solve these three unknowns. And now, if we want to solve yet another unknown, then we're going to need another equation. And this equation, in this case, is going to be the conservation of angular momentum. So how does this work? Well, just like the other three, we're going to find out what was the angular momentum at the start, and that has to be exactly the same as the angular momentum at the end. And then the only unknown in that case is going to be d, right? So no mystery there. What we do need to consider is what the angular momentum is going to refer. If we recall, we decided that positive was going to be upwards and then rightwards. But now, because we're dealing with momentum, we also need to decide whether we want to say this counterclockwise is going to be positive or clockwise is going to be positive. And it doesn't matter really, whatever you choose, as long as you stick with it, it's going to be fine. But let's do it intuitively, okay? So remember that the things were all spinning about, originally the ring G was here, and things were spinning about G, and they're all spinning in this direction here, right? Counterclockwise. And then the ring moved, and then the ring moved over here, and then it dissolved, like on the animation. So my question is, afterwards, how are the spheres spinning about this original point here, where the original G ring was? Well, again, intuitively, right? Hopefully you're going to see that A is going to spin this way here, so counterclockwise. C is going to spin this way here, so clockwise, and B as well this way here, clockwise. So that's hopefully a very intuitive way that this just makes sense to you just by looking at the velocities, okay? So just because we have two of them spinning counterclockwise and one spinning clockwise, sorry, other way around, two of them spinning clockwise and one counterclockwise, I'm going to say that my positive is the clockwise because we have two of those. Okay, but again, this is arbitrary. You can choose whatever you want. As long as you stick with it, that's fine. Okay, but this was very intuitive. So what I'm saying here is that if I'm calculating the angular momentum, and I'm going to go ahead and call this h naught, my angular momentum will be positive for the angular momentum of B, and also positive for the angular momentum C, and then negative for the angular momentum of A. Okay, so this is, again, very intuitive approach. Now, a bit of a better approach. The way that the angular momentum works, if you recall, is the angular momentum will be the mass, right? The mass of, just like the linear momentum, same idea, the quantity that we have, and the cross product, or the vector product, of my distance r, or my vector r, I should say, and my velocity. Okay, so this is just a general form of the angular momentum. Another way to think of this is to write it as the angular momentum, and now I'm just thinking about magnitude in this case here, is just my mass times my velocity, my distance r, and my velocity, as long as my velocity is perpendicular to my distance. Okay, so this is, if I'm only looking for magnitude, this is more straightforward. This one here I can rewrite as the mass times magnitude of r times magnitude of v times the sine of theta, the theta being the angle between the two vectors r and v. Okay, so we can use any of these approaches to solve this guy here. How can this make more sense? Well, my vector r is the one that leads from the point that I'm interested in. So in this case, where original G ring was, and that goes all the way to my sphere, right? So this would be my vector R here. And then what I want to ask, what I want to see is the angular momentum is going to be this guy, cross product of this guy and this guy. So that's going to create a momentum that's going like so, and which is a vector that's going out of the page, out of the screen, I should say, right, outwards. Well, that's one way to do it. The other way to think about this is, okay, let me break this vector R into two vectors, right? The one on the x direction and the one on the y direction. So actually, let me get rid of this, and let's just stay with the blue ones. Cool, so now I have two, and decompose that vector into two. Think about these vectors as strings holding the sphere. Okay, so think of this guy as one string holding the sphere A. Now, if my A is upwards, and I have this string happening here, how is this going to spin in relation to my original spot here? Okay, hopefully you see it's not going to spin whatsoever, right? It's going to try to go this way, and the string is just going to hold it in place, and it's not going to go anywhere, right? So it's not going to produce any angular momentum whatsoever. And this is because, and then again, another way to think of this is that because the angle between these two vectors here is 180, right? And if you go back to this definition here, sine of 180 is 0. So therefore, there's no angular momentum whatsoever associated with the combination of this vector Ry and my VA. Okay. On the other hand, if I take this vector now, my Rx, well, this now I do have, if you think again, think about the string analogy. Okay, if this is a string holding my bow A and I have velocity going that way, how is it going to spin in relationship to this point here? Well, it's going to go like so and around, right, all the way. Yeah, hopefully you agree. And then you see that this is spinning this way, so counterclockwise. So we're going to have a counterclockwise angular momentum associated with this. Again, the other way to think of it is if we're using this approach here, the angle now between the two, right, is exactly 90, and then the sine of 90 degrees is 1. So therefore, it's just the multiplication of this vector here times the velocity v, which is exactly this definition here, the black one, right? The mass times the vector times a velocity as long as the velocity is perpendicular to r. Okay, so these are all, I'm showing you different ways you can think of this and approach this, use whatever makes the most sense to you. Okay, so we found out that there's an angular momentum associated with A after the ring breaks, and this angular momentum is going to be, let's write it down. Which color will I use? Green. Angular momentum of A will be mass of A times r, this distance Rx, and I'm not sure what this distance is, I don't really care, and the velocity VA. Okay, we can do sine of 90 if you want. There's just one thing we need to remember, that we decided that counterclockwise is negative and clockwise is positive. So that means that because we just found out this is counterclockwise, that I need to put a negative here. This is a negative angular momentum. All right, so we're going to do the same thing with the other two, right? So if I want to do vector r, it's going to look something like this, and then perhaps it doesn't make much sense at first, so we're going to decompose it into two. One of them is going to be a ry is coming over here, and this ry in relationship to this place of interest here, it doesn't really matter because my velocity is going to go this way. The string Ry is not going to allow anything to happen, so no angular momentum related to this guy here. However, if we take another string and we place this string here like so, this is going to be my Rx, then you can hopefully see that this guy is going to rotate like so, right? So it's going to rotate all the way. Let's zoom out so we can see this happening real time. So taking this angle, it's going to rotate around this guy here. Yep. So the angular momentum produced by this is counterclockwise, and therefore, if I want to write it down, what I'm going to write down is that let's call this differently so that it's not the same name as we used for A. Let's call this Z for Z. Okay, and then if I want to write down the momentum here, the angular momentum, this is positive because it's clockwise, positive momentum, so positive. The mass of B times my Zx times my velocity B. Perfect. Last one. C. Okay, same exact thing. We would get a vector that goes from here to here. To make it easier for us to understand, we're going to break it down into two. And one's going to be this one, the other one's going to be this one. Hopefully, you can see straight off the bat that this one here, they don't really contribute to any angular momentum. These two, should do like this. They don't contribute to any angular momentum because as C is trying to go this way, the string is just going to hold it in place. It's not going to spin around this guy whatsoever. Yep. So this one, we don't care about it. We're interested in this one here, Ry. And this Ry, you can see hopefully that if this is a string holding C and the velocity is going that way, then the way it's going to spin this way. Yep, so it's going to spin that way. And then again, we said that this way here is positive. And then this means that my angular momentum regarding C will be R I, mass of C, positive, right? Positive mass of C, R Y times the velocity C. Okay, so we did like several different approaches all around the same topic. I just started with intuitive one. It might be enough for you. Then we did the different types. We did using cross product. We did only considering that we're only considering the ones that are when the velocity is perpendicular to r, and we can also use the idea that the cross product is just the two magnitudes times the sine of the angle between them. So in this case, again, this angle here is 90 degrees. If we consider the other vector there, then this angle here is 180. Sine of 180 is 0. Sine of 90 is 1. Cool. Okay. What else? What else? What else? What else we need to consider? Yes. So if we're taking the sine approach, one more thing that is probably useful to. Well, actually, let's just leave it as is for now. Okay. So everything we discussed so far is regarding the after, right? The after the ring breaks. So everything we talked about so far is for E angular momentum afterwards, correct? So let me sum up all the angular momentums afterwards, because after all, that's the idea, right? So what is the sum of angular momentums on the after the ring breaks? So we have, as a positive, we have mass of B times what we called Zx times the velocity B plus the mass of C, what we called Ry, and the velocity of C minus the mass of A times what we called Rx times the velocity of A. Okay, so at this point, it might make sense for us to rewrite this guy here as a function of this guy here, because what is quite obvious, hopefully, is that my Zx is just my Rx plus that distance there. And we happen to know that distance, right? It's been given from the start. So let's rewrite the vectors that we created here. So this is, I should probably done this on the bottom. This guy here. There you go. So this guy here is what we called Zx. Get rid of this. And then we also have this guy that we called Rx. And then it's hopefully that obvious that if I take Rx and I lower to this distance here, then I can see that what we called Zx is in reality just Rx plus that distance A that was given from the start. Okay, so I'm going to rewrite where I have this. I'm going to substitute this by Rx plus A. And probably need more space for this. Rx plus A. Okay, so this is the sum of all the angular moments that I have after the ring G dissolves. Cool, so what about before? So this is my before shot. Okay, what's going on before? Well, what's going on before is actually way simpler to calculate, right? Because we have every sphere going about ring G. And if you think about what's happening here is that the vector r, so the vector of the distance from the point about which they're rotating, and the velocity, right? So this is my RA, I guess. They always create a 90-degree angle, right? Because what's happening is that this vector here, vector velocity, is changing as my position of ball A is changing, right? So when my ball A is here, for instance, my vector is dead downwards, and then my vector RA is going to be like so. And what happens is that the angle is always 90 degrees between them. So this is way simpler for us to calculate, because if I want to know the angular momentum in this case here, the angular momentum in this case here is for A. For A is simply the mass of A times RA, which we happen to know it's 200 mils, times the velocity, the relative velocity that was given from the start. So what are we going to call that? Relative velocity. We're just going to put 0.8 that was given to us from the start. The relative velocity 0.8, which is this velocity here, right? What about this guy here? Well, this guy here doesn't have any angular momentum to it whatsoever, right? It doesn't have any distance. My R vector from point G to where V naught is 0. So therefore, there's no angular momentum associated with this guy here. Cool. What about the other one? Well, exactly the same thing, right? Mass of B times RB times the 0.8, which is the same. And then obviously C, exactly the same thing. Mass of C RC 0.8. So it's very, very simple, the one before. Obviously, if the other option here would be, to convert these things into into, you can do the same thing as we did before. You can, break my r vector into 2 if you wanted to, or the other option would be to break this velocity here into 2. We can have one like so and one like so. And then what we would have to do is, see the angle between this guy. Sorry, let me redo this. Between this guy and this guy, angle between this guy and this guy, and calculate the angles. So there's no need for that because we know it's always 90 degrees, and because it's always 90 degrees, it's always parallel. Sorry, perpendicular. And if it's also perpendicular, then we just need to multiply them to get the magnitude of the angular momentum. So if I sum up everything, so if I sum up these angular momentums here, what I'm going to have is the masses are all the same, so it's just 3 times the mass. Well, actually, let's do it in steps. So mass of A, remember that RA, RB, and RC, they're all 200 mils, so 0.2 meters times 0.8 velocity. And then mass of B, 0.2 meters for RB, and then velocity 0.8. And then mass of C, 0.2 meters and velocity 0.8. The masses are all the same, so this is just 3 times the mass. So 3 times the mass times the 0.2, which is the distance r, times the 0.8, which is the velocity. So as simple as that, right? So 0.48. So this is just 0.48 times the mass of one of the spheres. And then, obviously, what we're going to do is we're going to make these two guys equal, right? Because we're saying that the angular momentum is being conserved. There's no loss in energy whatsoever. So therefore, how can I do this? Let's do it here. So because, let's put it this way, because the sum of angular momentums before has to be equal to the sum of angular momentums afterwards, then what we're saying here is that this, well, actually what we can do is simplify before we put them together. We can actually simplify this one step further. So the sum of my afterwards, the masses are all the same. Let me think, the masses are all the same. We have all the velocities. So what we can do is take the mass out, and then we're going to have the velocity of A and B are the same. So I'm going to substitute where I have velocity of B, and just going to put velocity of A. Magnitude are the same. We already accounted for what's positive and negative according to the different directions. So let's say this is going to be Rx times VA plus A times VA plus this guy here, so Ry times VC minus this guy here, Rx times VA. So this is exactly the same as this, so they cancel each other out. So this is simplified into just a mass that multiplies A VA plus Ry VC. Brilliant. Ry is exactly what we're looking for. If you recall, what are we looking for? We're looking for this distance D. This distance D is exactly what we defined before as Ry over here. So therefore, what we're looking for is this value here. Same thing as D. So now let's go ahead and make the two things equal. What we're saying is that 0.48 times the mass of this whole thing, which is the angular momentum before the ring dissolves, has to be equal to the mass times A VA plus Ry or D, whatever you want to call it, D I guess, because that's the unknown I'm trying to solve, VC. The masses are the same, so as long as they're not 0, we can divide by the mass. All good. So this means that my D thing I'm looking for is 0.48 minus A times velocity A divided by velocity C. Cool. Okay, we have everything. We calculated the velocities before. We have the distance A. It was given in the problem statement. So all we need to do is plug and play, be happy about it. So let's put the numbers here. 0.48 minus distance A is 346 mils, so 0.346 meters. Velocity A we calculated before, and that was 0.693. And velocity C we know to be 1.2. And this gives us about 0.2. So distance D is approximately 200 mils. Cool. So what we did here is we used the angular momentum to actually solve the distance there. The distance actually is quite intuitive, right? If D is going perpendicular to my x-axis, if it's going perpendicular, then the ring must have dissolves when it was right here. So it's tangent coming out and going only horizontally. That would make a lot of sense. So 200 mils is the answer for distance d. To do that, what we did is we used the conservation of angular momentum, calculated the angular momentum of the whole system afterwards and the whole system before, made them equal. Now, there's one question that shows up a lot here, which is the following. Why did you consider y to be, why did you consider the same spot as before when calculating the aftermath? Couldn't you, create a new axis system? So I'm going to use this one that's less messy with less joints. Couldn't you create a new axis system that had, y here, for instance, and consider how things were spinning about y in this position here? So in this case, it would be, VA spinning over here, VC spinning over here, and VB spinning over here. Actually, yes, you could. Okay, you can do that. Yeah, you can actually solve. You're going to get exactly the same result. Nothing, no problem there. So I actually encourage you to do that on your own as an exercise to complement this one. Just remember that you're going to have a vector. Let's go our xb. Okay, it's going to be going rightwards. We're going to have a vector rxa. I'll be going there. They are both related by this distance a. These two vectors. And you're also going to have the same distance there d, which is our y for that matter. Okay, and then if you combine this this information here, you're going to get exactly the same thing as you got before. So I hope this was useful. I hope this was a good introduction to angular momentum conservation. We're going to be seeing more of this in the future. If you have any questions, just let me know. And if not, we'll talk soon.